Today we have He Kuo. He's going to be talking to us about Prague dimensions of random graphs.
All right, so thanks for an introduction and thanks for the organizing. Yeah, today I will talk about result based on joint work with Kellen Payton, who just talk about the result, and with my advisor, Luz Wonki. So actually we discuss more property of the clique covering in the random graphs. So what's the property we care about? So that is Prague dimension. So before I give you a formal definition, let me give you some intuition about the Prague dimension. Actually, the Prague dimension is related to these three aspects. So it is related to the problem or representation problem, where people are trying to find some efficient encoding of objects. And it's also related to the decomposition problem, as Kellen has talked about. So where people try to divide an object into the mean number of simpler objects. For example, we try to divide the edges of GNP into cliques, edges of cliques. Because the Prague dimension is kind of dimension where people try to embed an object into the mean number of one-dimensional objects. Okay, so I will introduce the formal definition of Prague dimension in the next slide. That was introduced by Nestrel, Porter, and Rodo in the late 1970s. Previously, there are many approaches have been applied to study Prague dimension, including algebraic, combinatorial, and information theoretical ones. So typically, it is NP hard to determine the Prague dimension of a graph. So as you can see, it's an interesting but difficult problem. In this talk, I will introduce the result that we resolve a Prague dimension conjecture of Rudy and Counter, so that we determine the order of magnitude of the Prague dimension of random graphs. Okay, then I think we can move on to give the definition of Prague dimension. So actually, there are many equivalent definitions, and I will give one that is useful for us. So here for a graph G, the Prague dimension of the graph G is the mean number k, such that there exists a k-colorable clique covering of the complement graph of G. So let me explain it word by word. So what is a clique covering? So as Kellen has talked about, so a clique covering of a graph is a collection of cliques that cover all the edges of the graph. So for example, if you have this graph, and as you can see, these colorable cliques, they make a clique covering because they cover all the edges of the graph. So they are clique covering. And what does it mean for the clique coloring to be k-colorable? So clique covering is k-colorable means that the cliques in the same color class are vertex disjoint. So if you have a clique covering, we need to give them different colors so that the clique in the same color class are vertex disjoint. For example, for those cliques, we give them some colors, red, blue, and yellow. And you can see that the cliques in the same color class are vertex disjoint. And actually for these three cliques, they must receive different colors because they share this vertex. So they need to be colored by different colors. Okay, so is there any question at this point about the definition of Prague dimension? Because that is important and it will be used over the talk. Okay, then try to avoid this complement of G. We just define the clique Roman number of G to be the minimum K such that there exists a clique covering of the graph G itself. Therefore, the clique Roman number is just the Prague dimension of the complement graph of G. Okay, then let's move on. And one thing I like to mention is that for those clique, for this Roman number of a clique covering, you can will the clique covering as a hypergraph. So for example, you can will these cliques as a hyper edge So the hyper edge corresponds to the vertex side of the clicks. So the click command number is just a click command number of the hypergraph. So you have this hyper edge, this hyper edge, this hyper edge, and you try to color the hyper edge so that the hyper edge in the same color class are vertex joint. So that's a relation between the click command number and the chromatic index of hypergraph. Okay, then that is the main problem we will talk about. So that is a conjecture by Freudian counter. So they conjecture that with high probability, the Prague dimension of random graph GMP has the order of magnitude n over log n for all constant p. Because when we know that when p equal to 1/2, the random graph Gn 1/2 just take all the n vertex graph uniformly random. So they conjecture that almost all the n vertex graph has Prague dimension roughly this one. And because Prague dimension of some graph can be as large as n-1, so their conjecture says that, oh, that is a rare case and should not happen very often. To prove this conjecture, actually is enough for us to prove that the click command number of GMP has this order of magnitude. Because by definition, we know that the Prague dimension of GMP is just the click command number of the complement graph of GMP. And because the complement graph of GMP just has the same distribution as the binomial random graph Gn 1 minus p. And if we can show this result for all constant p, then we will done. And again, the lower bound is simple. So we have some simple lower bound. That is because if we try to cover all the edges into maximum degree vertex, we need to cover them by clicks. So we need at least so many clicks. So here is the maximum degree of GMP, and omega GMP is just the maximum click size of GMP. So we need at least so many clicks to cover the edges, those edges. And because they all contain the fixed vertex, so they should receive, those clicks should receive different colors. Therefore, we need at least so many colors. Therefore, this is a lower bound of the click command number of GMP. So what we need to do is to prove an upper bound. And as you can see in this form, it means that for an upper bound, we should deal with the clicks of size roughly log n, which is very large, and that is a difficult point. We overcome the difficulty so that we prove that with high probability, the click command number of GMP has this order of magnitude. So this verifies the Prague dimension of Freudian counter. And this result can be extended to the case that is the probability P goes to 0. We can also deal with the edge partition variance as Kaden talked about. So we can require the click covering to be edge disjoint. So that is actually a stronger result than this one. What is the motivation for us to study this problem? Because we know that when P equal to 1/2, it takes all the n vertex graph uniform and random. So this property says that almost all the graph has Prague dimension and click command number of all of this order of magnitude. And is related to covering and decomposition problem. So previously, as Kaden talked about, Fries and Rees studies the minimum size of click covering. Freudian and counter studies the minimum maximum degree of the click covering. So again, you can view the click covering as a hypergraph, where each hyper edge is a vertex set of click. Right, so the maximum degree is just the maximum degree of the hypergraph. And as we discussed, the click command number is at least the maximum degree. So actually our result is stronger than this one. And we solve this problem by some random greedy paradigms. So because we are interested in an upper bound, we need to find a click covering that with click command number and most is this one. So to find the click covering, as Kaden talked about, we use the semi-random Nibor algorithm. So each time we include some clicks and then form a click covering, random clicks. So I like to focus on is the second step. So how do we bound the click command number of those clicks? Actually, we use some random greedy algorithm. Therefore, chromat number of the click covering is just as small as the chromat number of each collection of the clicks. So that is the first step, how to form the click covering, and Killian has talked about. And for the second step, what we really want to do is we want to prove that the click chromat number of each collection of clicks is at most some constant C times the maximum degree of the collection of clicks. Again, we will the collection of clicks as a hypergraph. And I promise that if we can prove this kind of result, then we will be done. This kind of result is kind of like the Perman-Spencer-like result. So what is Perman-Spencer result? So that is a result about the click chromat number and the maximum degree of a hypergraph. So their result states that for any constant k, at least for any constant k and any small epsilon, if you have a k-uniform hypergraph H that is nearly regular, which means almost all the vertex of H is in roughly the same number of edges and has small codegree, which means for any two vertex of H, they are in a small number of hyper edges. Then that proves that the chromat number of H is at most 1 plus little of 1 times the maximum degree of H. And recall that we have the trivial lower bound is that the click chromat number is at least the maximum degree of H, because for all the edges in the input vertex, they should receive different colors. Therefore, they prove that actually this chromat number is roughly the maximum degree of H. And we need this kind of result because they offer some constant like 1 plus epsilon. We need some constant like C. But the difficulty here is that actually we cannot use the Perman-Spencer result because they require the uniformity of the hypergraph to be a constant K. But for the clicks we include into each collection, they have size, they can have size as large as log n. So the uniformity of the hypergraph can be as large as log n. So we cannot use Perman-Spencer result. And that is a difficulty. And we overcome this difficulty because for each collection of clicks, there are some random set of clicks. We use the randomness so that we can extend to the uniformity that K can be as large as log n. So that is a key ingredient of our result, so that the chromatic index for random hypergraph. So the results stay like following. So if you have a host graph hypergraph H, which is K uniform and n-vertex hypergraph, it satisfies that the uniformity of the hypergraph is at most some constant B times log n. So the uniformity can be very large as log n. And it's nearly regular, which means for almost all the vertex of H, it's roughly in the same number of hyper edges. And it has small codegree, which means for any two vertex of H, it is in a small number of hypergraphs. So if your host graph H satisfies these properties, and then you have a random subhypergraph Hi that take m edges uniform and random. So the m is not too small, much less than the total number of the host edges. Then we can prove that with high probability, the click chromat number of the random hypergraph Hi is at most 1 plus some delta times the maximum degree of the random hypergraph Hi. So here you delta satisfies this relation. The key point is that the uniformity here can be as large as log n. So for example, if you K is little log n term, then you know that this B can be little of 1, therefore delta is little of 1. Therefore, you really get some Perman-Spencer-like result, 1 plus little of 1 term. But what we need is we use K is bigger of log n term, so the constant B may be large, and then your delta is some large constant, so we get this kind of result. And that will be enough for us to prove the Prague dimension, to prove the click chromat number result. And to prove this chromatic index of, chromatic index for random hypergraph result, we use some random gradient algorithm. So that means we have so many available colors. And at each round, we sample one random edge, and we color it by a available color, which means that color is not used in any previously sampled edge that incident to the current edge. So we just color it by an available color, and we prove that this random greedy coloring algorithm actually can properly color the HM properly. Therefore, we prove our result. So that's a high-level idea to prove this result. So as a summary, we prove that with high probability, the Prague dimension has order of magnitude n over log n for all constant p. So that verify a conjecture by Freudian counter. And our proof contains two parts. First part is we use semi-random algorithm to find a click covering, as Keelan has talked about. And then we use a random greedy algorithm to color the clicks in each collection. So the new tool here is the chromatic index result for random hypergraph, which allows the uniformity of hypergraph can be as large as log n. Yeah, because here we determine the order of magnitude. Open problem is what is asymptotics. All right, so let me stop here. Thank you.
All right, thank you very much. Let's briefly thank the speaker. Are there any questions for the? So one question for me, what are the, so you mentioned this last problem here, there are gaps when p tends towards 0. What are the gaps like? What's it between?
Okay, so the gaps is because for the trivial lower bound, we have this kind of trivial bound, the maximum degree over the maximum size of it. But actually when p tend to 1 for the click chromatic number, actually this trivial lower bound does not hold. So you can show that there exists some function, the function, so that this function times this part. But for this function, actually this function tend to 1 as p, tend to infinity as p tend to 1. So it means this order of magnitude is no longer true when p tend to 1.
I see.
Yeah. So that is. Also, that is a difficulty for the other part. And for the gaps, because for some p we can actually determine, that is for when p tend to 1, and actually when p tend to 0, we determine the asymptotics of these parameters. But there are some gaps, some logarithmic gap, I think.
Okay.
Yeah, when according to p.
Okay. Other questions? One other brief one for me. So you use this like uniformity like version of or the higher uniformity version of Spencer's result.
Yeah, it's kind of a result, but their result does not extend to the large uniformity. Actually,
Right. Yeah. But so at least naively to me, it seems like you would apply this to non-uniform hypergraphs because the peaks you get aren't, just all the same size. So do you actually need a non-uniform version of this? And is that just applied by the uniform version?
No, actually we use the uniformity version.
Okay, it's uniform.
So
okay.
Actually, yeah, for the clicks, because as Keelan said, we mainly take about the large clicks, which has the same size actually.
I see, and it's just like edges besides that. Okay, that makes sense. Okay, cool. Any other last questions, comments? All right, if not, let's thank the speaker one more time.